Holm 15. Alpha does not announce itself with blazing spiral arms or glittering clusters of newborn stars. It resides in a galaxy that appears swollen and diffuse, a pale giant embedded in the dense environment of a galaxy cluster more than 700 million light-years from Earth. At first glance, it seems quiet, almost inert, yet careful observation reveals that its light is stretched thin across an enormous volume, as though the galaxy has been stirred and diluted over billions of years. That subtle distortion is the beginning of our investigation. Holm 15 Alpha lies at the heart of a galaxy cluster known as Abell 85. A galaxy cluster is a gravitationally bound congregation of hundreds or even thousands of galaxies, along with vast reservoirs of hot gas and an even larger halo of unseen dark matter. In such environments, gravity does not operate politely. It drags, strips, and merges galaxies together in slow collisions that unfold over hundreds of millions of years. Central cluster galaxies, often called brightest cluster galaxies, are the final repositories of this relentless merging. They grow bloated and massive by consuming neighbors whose stars are torn free and absorbed. Holm 15. Alpha fits this description, but it exceeds expectations. Its visible stars extend across a region so large that astronomers describe its core as unusually shallow. Normally, as one approaches the center of a massive galaxy, the density of stars increases sharply. In Holm 15 Alpha, that increase is far less steep than models would predict. The central light profile appears scooped out, as though something has evacuated stars from the innermost region. This is where curiosity sharpens into tension. What process could remove stars from the gravitational heart of one of the most massive galaxies in the nearby universe? To understand the significance of that question, we need to consider how black holes are thought to inhabit galaxies. Observations over the past decades have established that nearly every large galaxy hosts a supermassive black hole at its center. A supermassive black hole is a compact region of space-time containing millions or billions of times the mass of our Sun, compressed into a region smaller than our solar system. Its defining boundary is the event horizon, the distance from the center at which the escape velocity equals the speed of light. Inside that boundary, no signal can return. In ordinary massive galaxies, these black holes influence only the innermost stars. Their gravitational sphere of influence, meaning the region where their gravity dominates over that of the surrounding stars, typically spans a few dozen light-years. Beyond that scale, the galaxy's collective mass overwhelms the pull of the central object. But what if the central object were far more massive than usual? What if its sphere of influence extended not tens, but hundreds, or even thousands of light-years? In that case, its presence could reshape the structure of the galaxy's core in a measurable way. Astronomers first suspected something unusual in Holm 15 Alpha when detailed imaging revealed the shallow brightness profile. Using large ground-based telescopes equipped with sensitive spectrographs, instruments that disperse light into its component wavelengths, they began to measure the velocities of stars near the center. When starlight is stretched or compressed in wavelength due to motion along our line of sight, a phenomenon known as the Doppler effect, it reveals how fast those stars are moving toward or away from us. The logic is straightforward but profound. The faster stars move in orbit around the galactic center, the more mass must be enclosed within their orbits. Gravity provides the centripetal force that keeps stars bound. Stronger gravity requires higher velocities for equilibrium. By mapping stellar speeds at different distances from the center, astronomers can reconstruct the underlying mass distribution. In Holm 15A, the stellar velocities near the core were extreme. Models that attempted to reproduce those velocities using only the mass of visible stars fell short. Even after accounting for dark matter, the invisible component inferred from gravitational effects on large scales, the central gravitational pull remained too strong. The simplest explanation was the presence of a black hole of staggering mass. Estimates place this object at tens of billions of times the mass of the Sun. To place that in context, the black hole at the center of our Milky Way galaxy contains about 4 million solar masses. Even the famous black hole in the galaxy Messier 87, whose silhouette was imaged in detail, is measured at roughly 6.5 billion solar masses. Holm 15 Alpha appeared to host something several times larger still. Such an object falls into a category often called ultramassive black holes. The term is informal, but it conveys scale. These are black holes whose masses approach or exceed 10 billion solar masses, rivaling the mass of small galaxies themselves. Their existence pushes against the boundaries of standard models of galaxy formation, yet caution is essential. Measuring black hole masses at such distances is extraordinarily challenging. The galaxy's distance means that even powerful telescopes cannot resolve individual stars. Instead, astronomers analyze the integrated light from vast numbers of stars blended together. They construct dynamical models, mathematical representations of how stars move under gravity, and adjust parameters until the predicted velocity distribution matches the observed data. Each assumption introduces uncertainty. Evidence suggests that the shallow core of Holm 15A may be the fossil imprint of past black hole mergers. When two galaxies collide, their central black holes sink toward the merged center due to dynamical friction, a process in which gravitational interactions with surrounding stars rob them of momentum. Eventually, the two black holes form a binary system, orbiting each other. As this binary tightens, it can eject nearby stars through gravitational slingshot interactions, effectively carving out a depleted region in the stellar distribution. If Holm 15A has undergone repeated mergers over billions of years, its central black hole may have grown by swallowing others. Each merger would enlarge the binary and expel additional stars, deepening the central core. The unusually large and shallow core we observe today may therefore be indirect evidence of an extraordinary growth history. Still, we must separate what is observed from what is inferred. The observed facts are the galaxy's diffuse central light and the high stellar velocities measured through spectroscopy. The inference is that only an ultramassive black hole can reconcile these data. Alternative explanations, such as unusual distributions of dark matter or anisotropic stellar motions, have been explored. Models indicate that while these factors contribute, they cannot fully account for the magnitude of the effect without invoking a central object of immense mass. As our telescopes refine their measurements, the case strengthens, yet the image remains indirect. We do not see the black hole itself. We see its gravitational choreography. We see stars compelled into rapid orbits and a core scraped clean by past interactions. Gravity is the only messenger. And so, the journey becomes one of reconstruction. We stand far from Holm 15A, separated by hundreds of millions of light years and countless intervening galaxies. The light entering our instruments tonight left that cluster when dinosaurs still walked the Earth. In that ancient light lies a record of motion, and in that motion lies mass. But mass alone does not tell us what this object is like. A black hole of tens of billions of solar masses is not simply a scaled-up version of smaller ones. Its event horizon would span a region larger than our solar system. Its gravitational influence would extend across a significant fraction of the galaxy's core. Its growth history would reflect some of the most violent processes in cosmic evolution. To understand how such a giant could form, and whether our measurements truly capture its scale, we must next examine the methods used to weigh something that emits no light at all. We must translate shifts in spectral lines into a mass that warps space-time itself. The question now is not merely whether Holm 15A hosts an ultramassive black hole, but how confident we can be in that conclusion. The evidence rests on motion, and motion, measured precisely enough, can expose even the darkest presence. In the next step of this investigation, we turn fully to the techniques that transform faint starlight into a cosmic scale capable of weighing one of the largest black holes ever observed. To weigh a black hole is to accept a paradox. The object itself cannot be seen, yet its mass can be measured with remarkable precision if you know where to look for the distortion it causes. In Holm 15A, the primary evidence comes from stars whose light reaches us as a blended glow. Those stars are not simply sitting in place, they are moving in response to gravity. The first task is to turn that glow into a map of motion, and the second is to separate the gravitational contributions of everything else in the galaxy from the one influence we care about most. Astronomers begin by collecting spectra from the galaxy's central region. A spectrum is a measurement of how much light arrives at each wavelength, and it is rich with absorption features, narrow dips created when atoms in stellar atmospheres absorb specific wavelengths. And these absorption features function like reference markers. When a group of stars moves toward us, its absorption features shift slightly toward shorter wavelengths. When it moves away, they shift toward longer wavelengths. This shifting is the Doppler effect, and it translates motion into a measurable change in the light itself. But the center of Holm 15A is not a single star with a clean signal. It is a crowded field containing billions of stars, each with its own orbit and velocity. Their individual spectral lines overlap, and instead of shifting as a single tidy set, they broaden. The amount of broadening encodes the spread of velocities in the stellar population along our line of sight. Astronomers call this measurement the velocity dispersion, a statistical description of how widely the stellar speeds are distributed. Higher velocity dispersion implies stronger gravity binding the stars, because stars in a deep gravitational potential well move faster and in a wider range of orbits. Velocity dispersion alone is not enough. Two different mass distributions can produce similar dispersions if the stellar orbits are arranged differently. A population of stars moving mostly in circular paths can mimic the dispersion of a population moving on elongated radial trajectories. This is the core difficulty. We see only the component of motion along our line of sight, and even that is averaged over many stars. To solve the problem, astronomers must build models that explore possible orbit families and ask which combinations can reproduce the observed spectra. These dynamical models are the engine of the measurement. The guiding principle is cause and effect. Mass creates gravity. Gravity shapes orbits. Orbits determine velocities, and velocities reshape spectra. If a model predicts the same spectral broadening and the same detailed shape of the absorption features that the telescope actually records, then the mass distribution inside the model is a plausible representation of the real galaxy. The most widely used approach for galaxies like Holm 15A involves constructing a library of orbits inside a proposed gravitational potential. The gravitational potential is the map of how strongly gravity acts at each point. It is determined by the distribution of mass, including stars, dark matter, and a central black hole if one is present. For each proposed potential, a computer generates many possible stellar orbits, ranging from nearly circular to highly elongated. It then assigns weights to these orbits so that, when combined, they reproduce the observed brightness distribution of the galaxy. This step matters because the model must match what is directly observed, the way starlight is distributed across the image. Once the model matches the light, it is tested against the spectroscopy. The weighted orbits predict a specific pattern of line-of-sight velocities at different positions. These predictions are compared to the measured spectra across the galaxy's core. The model is adjusted not by changing the orbits themselves arbitrarily, but by changing the underlying mass distribution and repeating the process. Over many iterations, the model converges on a range of black hole masses and stellar mass values that produce the best match. This method is careful, but it is not immune to uncertainty. One major source of uncertainty is the stellar mass-to-light ratio, the conversion factor between how much light we see and how much mass the stars actually contain. A galaxy can be bright because it has many stars, or because its stars are younger and more luminous, or because its stellar population has a different mix of low-mass and high-mass stars. In a massive central cluster galaxy like Holm 15A, the stellar population is expected to be old, dominated by long-lived, lower-mass stars. Even so, the exact mass-to-light ratio must be inferred, often using stellar population models calibrated by the spectrum itself. If the mass-to-light ratio is slightly misestimated, the inferred black hole mass can shift, because the model must decide how much of the gravitational pull near the center comes from stars versus the black hole. Another source of uncertainty is dark matter. Dark matter is a form of matter inferred from gravitational effects, but not detected through emitted or absorbed light. In galaxy clusters, dark matter dominates the total mass. In the inner regions of galaxies, stars can dominate, but in a central cluster galaxy embedded in a vast dark matter halo, the dark matter contribution may still be significant. If the dark matter density rises steeply toward the center, it can mimic some of the gravitational signature attributed to a black hole. Models therefore include a parameterized dark matter halo and allow it to vary within plausible ranges. The aim is not to force the black hole to be huge, but to test whether any reasonable combination of stars and dark matter can explain the observed velocities without a giant central object. In Holm 15A, models indicate that even with dark matter included, a very large central mass concentration is needed to reproduce the inner kinematics. That pushes the inference back toward an ultramassive black hole. The observations themselves impose limits. The key region for measuring a black hole is its sphere of influence, the zone where its gravity overtakes that of the surrounding stars. In practice, this means that the telescope must resolve, at least partially, the area where the black hole's pull creates a distinct rise in velocity dispersion or a change in the velocity distribution. If the sphere of influence is smaller than what the telescope can resolve, the measurement becomes uncertain because the black hole's effect is smeared out across the instrument's resolution element. Here, the suspected size of the black hole becomes both a challenge and an advantage. A black hole of tens of billions of solar masses would have a relatively large sphere of influence, potentially spanning hundreds of light years. At the distance of Holm 15 alpha, that scale is still tiny on the sky, but it may be just large enough to imprint a measurable signature on the spectra collected from Earth-based telescopes under good conditions. The measurement is still delicate. The atmosphere blurs images, and even with advanced correction techniques, the central region is not perfectly resolved. This is why astronomers emphasize that the black hole mass is an estimate, constrained by the data, rather than a single exact number. The data support a very large mass, but the uncertainty range can be wide. Another subtlety comes from the galaxy's geometry. Dynamical models must assume a three-dimensional shape to translate the two-dimensional image into a true mass distribution. Many models assume axial symmetry, meaning the galaxy is roughly symmetric around a central axis, but brightest cluster galaxies can be triaxial, shaped more like a stretched ellipsoid than a simple flattened sphere. If the true shape differs from the model assumptions, the inferred orbit distribution can shift, which can in turn affect the estimated black hole mass. Researchers address this by exploring different plausible geometries and by checking whether the best-fitting solutions remain consistent. If a giant black hole is required across many plausible geometries, confidence increases. In Holm 15 alpha, the shallow core adds another critical constraint. A depleted stellar core is not merely a visual curiosity, it alters the gravitational potential near the center. If stars have been ejected by past black hole binaries, then the stellar mass density in the core is lower than it would otherwise be. That means there is less stellar gravity to account for the observed stellar velocities. In a sense, the core makes the black hole easier to detect dynamically, because the stars cannot hide its influence as effectively. The same feature that first raised suspicion, the scooped-out light profile, also reduces degeneracy in the mass model by limiting how much mass can plausibly be attributed to stars in the center. Yet responsible analysis must entertain competing explanations. Could the core be produced by something other than black hole mergers, such as the dynamical heating of stars by repeated galaxy interactions in the cluster? Could the velocity measurements be biased by subtle observational effects, like contamination from stars at different depths along the line of sight? Could the galaxy contain a complex mix of stellar populations with different mass-to-light ratios across the core? These possibilities are examined through careful observational strategy. Spectra are taken at multiple positions and compared for consistency. The measured velocity dispersion profile, how dispersion changes with distance from the center, is compared to theoretical expectations for different mass models. If the profile rises sharply toward the center, that is a classic indicator of a central mass concentration. If it is flat or declining, it suggests stars dominate and the black hole influence may be smaller. In Holm 15 alpha, the inner kinematics have been interpreted as consistent with an extremely massive central object, though the precise shape of the profile and its uncertainties remain active areas of discussion in the field. There is also the broader context of scaling relations. In many galaxies, the mass of the central black hole correlates with properties of the host galaxy, such as the velocity dispersion of stars in the bulge and the mass of the bulge itself. These correlations likely arise because black hole growth and galaxy growth are linked through processes like gas inflow star formation, and energetic feedback from active galactic nuclei, where a black hole accretes matter and releases enormous energy. If Holm 15A truly hosts a black hole of tens of billions of solar masses, it may sit above the standard correlations, suggesting that central cluster galaxies and their black holes may follow a different evolutionary pathway. That tension is not a reason to reject the measurement. It is a reason to investigate whether the environment of galaxy clusters produces outliers and whether our correlations are incomplete at the extreme high mass end. Weighing the black hole therefore becomes not only a technical challenge, but a test of cosmic history. If the mass is indeed that enormous, it implies a growth process that operated efficiently over cosmic time. One pathway is repeated merging of black holes during the assembly of the central cluster galaxy. Another is sustained accretion of gas during earlier epochs, when the universe contained more cold gas and galaxies were more actively forming stars. Models indicate that the most massive black holes likely grew through a combination of both. Episodes of rapid feeding, punctuated by mergers that combined already massive black holes into an even larger remnant. But even this synthesis must be treated carefully, because the details matter. Accretion can be limited by radiation pressure, the outward force of light emitted by hot gas as it falls in. If the black hole feeds too quickly, the radiation can push back on infalling matter and slow the process. Mergers, meanwhile, are not guaranteed to add mass cleanly. When two black holes merge, they emit gravitational waves, ripples in space-time that carry away energy. That energy loss slightly reduces the final mass compared to the sum of the two initial masses. In addition, the merger can impart a recoil kick to the remnant, potentially displacing it from the galactic center. In a shallow core like Holm 15A, where the gravitational potential near the center is less steep, a recoil could push a merged black hole off-center for a long time before it settles back. Evidence for such displacement would be subtle, but it is part of the complex physics that must be considered when interpreting the galaxy's core. All of this might sound like an exercise in abstract modeling, but the tension is real. If the black hole is that massive, then its event horizon is not a theoretical boundary. It is a physical region of space, large enough to dwarf planetary systems. Its gravity does not merely bend the paths of nearby stars, it shapes the inner architecture of the galaxy. And the only way we know that is because the light from distant stars, filtered through their absorption lines, carries the imprint of their speed, and their speed carries the imprint of the mass that commands them. By the end of this weighing process, the measurement is not a single number etched in stone. It is a range bounded by the data and by the assumptions that remain plausible. The most careful phrasing is therefore restrained. The evidence suggests that Holm 15A hosts one of the most massive black holes known, with an estimated mass in the tens of billions of solar masses, though the exact value depends on modeling choices and the limits of current resolution. Yet a mass estimate, even a cautious one, invites a deeper question. What does a black hole of that scale do to space-time? What does it mean to approach a boundary where even light cannot escape, when that boundary is larger than the orbit of Neptune? The measurements give us weight. The next step is to translate weight into structure, to understand the geometry of the trap itself. The deeper we go, the less the galaxy feels like a collection of stars, and the more it feels like an arena where space-time is the main actor. That is where our journey turns next. If you could erase every star from Holm 15A and leave only its gravity behind, the cluster would still feel it. The galaxy's heart would still warp the paths of nearby matter. That is the unsettling clarity of black holes. They can be hidden from every camera, yet their presence shapes the cosmos with a certainty that is almost tactile. To approach the black hole in Holm 15A is not to imagine a plunge through darkness, but to understand a geometry that becomes increasingly unfamiliar as distance shrinks. Gravity in everyday life is a force that falls with distance. In the vicinity of a supermassive black hole, gravity is still governed by the same underlying principle, but the scale changes the experience. Space-time, the four-dimensional fabric that combines 3 dimensions of space with time, becomes curved so sharply that the usual intuition about motion begins to fail. The first specialized term we must define is the event horizon. The event horizon is the boundary around a black hole where the escape speed reaches the speed of light. Outside it, a sufficiently powerful rocket could, in principle, climb away. Inside it, no propulsion, no signal, no physical process can move outward fast enough to counter the inward pull of space-time itself. The event horizon is not a solid surface. It is a threshold in the geometry of space-time. Crossing it does not feel like hitting a wall. The strangeness is that it feels locally like nothing at all, while it changes your future with finality. For an ultramassive black hole, the event horizon is enormous. For a black hole of tens of billions of solar masses, models indicate an event horizon whose diameter would be comparable to the scale of our outer solar system. This matters because it changes what tidal forces do near the horizon. Tidal forces are the differential gravitational pull across an object. The part closer to the black hole is pulled more strongly than the part farther away. In smaller black holes, tidal forces near the horizon are so intense that they can tear apart stars or even atoms. In ultramassive black holes, the horizon lies far enough from the central singularity that the tidal gradients at the horizon can be much gentler. The paradox is that the largest black holes can be, in one narrow sense, the least violent at the boundary, even while they remain absolute traps. Yet that gentleness is deceptive. The danger is not only in being torn apart. The danger is in what happens to time and causality as you approach the horizon. To a distant observer, an object falling toward a black hole appears to slow down. This is gravitational time dilation. Strong gravity slows the passage of time relative to regions farther away. The light from the infalling object is stretched to longer wavelengths, becoming redder and dimmer as it climbs out of the gravitational well. From far away, the object seems to freeze near the horizon, fading into darkness. But for the infalling traveler, time continues normally. They cross the horizon in a finite amount of their own time, and once inside they cannot turn back. This is not metaphor. It is a consequence of how space-time is shaped by mass. The black hole does not simply pull objects inward as a classical force. It alters the structure of possible paths, called geodesics, that matter and light can follow. In strong curvature, the inward direction becomes less like a choice and more like a future destination. Now place that concept back into Holm 15A. An ultramassive black hole does not exist in isolation. It sits within a galaxy, surrounded by stars, gas, and perhaps a halo of dark matter. The boundary of the event horizon is not the boundary of influence. Long before you reach it, the black hole's gravity dominates the orbital architecture of the inner core. In a typical galaxy, the central black hole's influence is confined to a region that might contain a few million stars. In Holm 15A, a black hole of tens of billions of solar masses would govern a region so large that the entire central stellar core becomes its stage. This helps explain why the galaxy's core can be so shallow. If a binary black hole existed there in the past, it would have interacted with stars across a broad volume, ejecting them and reducing the central density. Over time, the core becomes a low-density cavity in which the black hole's presence is implied by what is missing as much as by what remains. That cavity, however, is not empty. Even a depleted core contains stars, and those stars become test particles tracing the gravitational landscape. Their orbits can be distorted in subtle ways. Some may become elongated, plunging close to the center before swinging back outward. Others may settle into more circular trajectories depending on the galaxy's history. The shape of these orbit families, inferred from dynamical modeling, is an indirect view of the black hole's dominance. But there is a second actor in this environment: gas. Not every supermassive black hole is actively feeding today. Many are quiescent, surrounded by hot, tenuous gas that circulates without falling in efficiently. Yet, in a galaxy cluster, there is an immense reservoir of hot intracluster gas, heated to tens of millions of degrees by the cluster's gravitational compression and by shock waves from mergers. This gas emits strongly in X-rays. The center of the cluster, where Holm 15A resides, is often the densest region of that hot atmosphere. Gas there can cool, lose pressure support, and drift inward. If it reaches the vicinity of the black hole, it can form an accretion flow. Accretion is the process by which matter falls into a black hole. It rarely falls straight in. Instead, because infalling gas typically carries angular momentum, it forms a rotating structure called an accretion disk. In the disk, friction and magnetic turbulence cause gas to lose angular momentum and spiral inward. As it does, gravitational energy is converted into heat. The inner disk can become so hot that it emits intense ultraviolet and X-ray radiation. In the most active phases, this radiation can outshine the entire host galaxy, producing a phenomenon known as an active galactic nucleus. Here is the critical cause and effect chain. The black hole's gravity pulls gas inward. The gas heats up as it spirals closer. The heated gas emits radiation. That radiation can push outward on surrounding gas, regulating further inflow. In addition, the accretion disk can launch jets, narrow beams of particles accelerated to near-light speed by magnetic fields. These jets can inflate bubbles in the surrounding hot gas, stirring and heating it. Over time, this feedback can prevent gas from cooling too rapidly, suppressing star formation and altering the evolution of the galaxy. In the context of Holm 15A, such feedback may have played a role in shaping the galaxy's present-day quietness. Central cluster galaxies often show evidence of repeated outbursts from their black holes, visible as cavities in X-ray images of the intracluster gas. These cavities indicate that jets have deposited energy into the cluster atmosphere. If Holm 15A's black hole is ultramassive, its potential energy reservoir is immense. Even a modest rate of accretion could yield significant feedback power, influencing not only the galaxy, but the surrounding cluster core. Yet we must be careful with claims. The existence of an ultramassive black hole does not automatically imply current activity. A black hole can be massive and still dormant if it lacks fuel. Evidence suggests that many of the most massive black holes today are relatively quiet because the universe has less cold gas available than it did in earlier epochs. The cluster environment supplies hot gas, but hot gas does not always accrete efficiently. It may remain in a quasi-stable atmosphere, with only slow trickles reaching the center. So how do we translate the abstract geometry of the event horizon into something observationally grounded for Holm 15A? We look for signatures of influence beyond stellar velocities. We look for the footprint of feedback in the surrounding gas. We look for the structural consequences of past mergers. Consider again the binary black hole scenario. When two black holes orbit one another, they can harden, meaning their separation shrinks by interacting with stars. Each close encounter can fling a star outward at high speed, carrying away energy and angular momentum. Over many encounters, the binary tightens and the core loses stars. Eventually, when the separation becomes small enough, gravitational waves dominate the energy loss and the black holes merge. The merger releases a burst of gravitational waves that carry away energy and can produce a recoil kick. The remnant black hole may oscillate through the core, further heating and rearranging the stellar distribution. This chain predicts a particular signature, a large, depleted core correlated with a large black hole mass. Holm 15A shows precisely such a core. That correlation is one reason astronomers take the mass estimate seriously. The galaxy's structure and its inferred central mass tell a consistent physical narrative, not a poetic one, but a mechanistic one. Mergers and gravity slingshots produce cores. Repeated mergers build mass. Mass deepens the gravitational potential. Deep potentials drive high stellar velocities. Yet the most eerie aspect remains the event horizon itself. In everyday environments, there is always a way out, at least in principle. A black hole ends that principle at a definable boundary. In the case of an ultramassive black hole, that boundary becomes almost macroscopic by cosmic standards, spanning billions of kilometers. A region of space that large in the center of a galaxy is permanently hidden from the rest of the universe. Everything that crosses the horizon becomes causally disconnected from the outside. If Holm 15A's black hole truly has this scale, then at the galaxy's center there is a volume larger than a planetary system from which no information returns. Yet around it, stars orbit, gas circulates, and light continues to travel outward, carrying only indirect evidence of the abyss. This is where the journey changes tone. Up to now, we have relied on measurable motion and the careful inference of mass. Now we confront what that mass means. The black hole is not just heavy. It is a region where the rules of escape fail. It is a demonstration that gravity, when concentrated enough, can alter the topology of space-time. And it forces another question, larger than Holm 15A itself. If ultramassive black holes exist, how common are they? Are they rare accidents, the result of unusual merger histories in the densest clusters, or are they the natural endpoints of galaxy assembly at the highest masses? Do they fit within our current understanding of cosmic growth, or do they require new pathways, perhaps involving the rapid formation of massive seed black holes in the early universe? To answer that, we cannot remain at the event horizon. We must widen the frame again and compare Holm 15A with other extremes. We must test formation scenarios against evidence from many galaxies, and we must look ahead to the next generation of observations that could confirm this black hole's mass more decisively or reveal a different explanation. Because in astrophysics, even the most imposing object is measured not by our awe, but by how well it fits the evidence. The next section follows that evidence outward, from one galaxy's core to the broader population of cosmic giants, and toward the questions that remain unresolved. Holm 15A is compelling, not because it is mysterious in the casual sense, but because it sits at a fault line between what we can measure and what our broader models predict. If its central black hole truly weighs in the tens of billions of solar masses, then it belongs to a small class of objects that do not simply extend the known distribution, they interrogate it. They force us to ask whether the most massive galaxies and the most massive black holes share the same growth rules as everything below them, or whether the high end of nature's scale operates by different constraints. To widen the frame, astronomers compare Holm 15A with other galaxies suspected of hosting ultramassive black holes. The most famous examples tend to be central cluster galaxies and the largest elliptical galaxies. This is not a coincidence. In the hierarchical picture of cosmic structure, small systems merge into larger ones over time. Galaxy clusters are the most massive bound structures in the universe today, and their central galaxies are the final beneficiaries of that merging. If any galaxies are expected to grow black holes beyond the ordinary supermassive range, it is those that have spent billions of years at the gravitational crossroads of a cluster. But expectation is not proof. The difficulty is that the measurements become harder as distance grows and as the targets become more diffuse. Even with the largest telescopes, the dynamical signature of a black hole is subtle at great distances. The same data that hint at a giant can, if interpreted differently, yield a less extreme mass. This is why Holm 15A remains a point of active scrutiny. It is a test case for how confidently we can measure the most extreme black holes using stellar dynamics alone. There is, however, a second line of evidence embedded in the galaxy's architecture, the core itself. In many massive galaxies, there is a relationship between the size of a depleted stellar core and the mass of the central black hole. The physical mechanism is the gravitational slingshot ejection driven by black hole binaries. When two black holes orbit, they preferentially interact with stars whose orbits bring them close, and those stars receive energy and are thrown to wider orbits or even expelled from the galaxy's central region. This excavates a core. Repeated mergers deepen and enlarge it. Models indicate that the mass deficit in the core, meaning the amount of stellar mass missing compared to a steep, unscoured profile, can be several times the mass of the merged black hole system. That relationship is not exact because it depends on merger details, orbital structure, and the presence of gas, but it gives a consistency check. Holm 15. Alpha's unusually large core is therefore not a decorative detail. It is a forensic clue that points toward a very large central black hole and a violent merger history. Yet core size alone cannot determine the mass. The same scouring process might occur in different ways, and cluster environments can complicate the picture by repeatedly disturbing the galaxy's structure. So, the strongest approach is convergent. Dynamical measurements of stellar motion, structural evidence from the light profile, and environmental context from the galaxy cluster, all pointing in the same direction. Holm 15. Alpha is persuasive because these strands align, even while uncertainties remain. The next question is origin. How does nature build something so massive? One pathway is incremental, through mergers and accretion over cosmic time. Imagine an early universe where galaxies were smaller but richer in cold gas. Cold gas can fall toward galactic centers, fueling rapid black hole growth. During that era, black holes could spend episodes in an active phase, accreting efficiently and radiating intensely. As the surrounding galaxy also grows, the black hole mass climbs in step. Later, as galaxy clusters assemble and gas becomes hotter and less able to cool, accretion slows. Growth continues primarily through mergers. Galaxies collide, their black holes sink, binaries form, and eventually mergers add the masses together. This pathway seems plausible, but it faces a constraint: time. To reach tens of billions of solar masses, a black hole must have either started from a very massive seed or experienced sustained growth that avoided long interruptions. In standard scenarios, black holes begin as remnants of massive stars, with masses tens of times that of the Sun. Building from that to tens of billions requires not only a long time, but a high efficiency of feeding. Radiation pressure can limit accretion, and feedback can blow away fuel. The straightforward incremental path may therefore be too slow unless the black hole's early growth was unusually favored. That leads to the concept of massive seeds. A seed black hole is the initial black hole from which later growth proceeds. Models indicate that in the early universe there may have been channels for forming seeds far heavier than stellar remnants. One possibility is the direct collapse of a massive gas cloud into a black hole without first fragmenting into many stars. If a protogalactic cloud is dense, hot enough to avoid efficient cooling, and not enriched with heavy elements that encourage fragmentation, it might collapse more coherently, producing a seed black hole of tens of thousands or even millions of solar masses. Such a seed would give the growth process a head start. Evidence for this channel remains indirect, but it is actively explored because it can help explain how very massive black holes appear already in the early universe. Holm 15A, however, is not an early universe object in terms of our observation. We see it at a relatively modest distance in cosmic terms, long after most galaxy formation has played out. Its value is not that it reveals the early seed directly, but that it constrains what seeds and growth histories must have been possible. If an ultramassive black hole exists here today, then the universe has, at least once, executed a sequence of events that made it. Our models must account for that sequence without breaking other constraints, such as the observed population of black holes at lower masses. There is another possibility that makes Holm 15A even more provocative: that the largest black holes and their host galaxies may not follow the same scaling relations as ordinary systems. In many galaxies, black hole mass correlates with stellar velocity dispersion and bulge mass. These correlations are often interpreted as evidence of coevolution regulated by feedback. But in the central galaxy of a cluster, growth can be dominated by dry mergers with little cold gas. Dry mergers add stars and black holes without triggering much new star formation. They can inflate the galaxy's size and mass while changing velocity dispersion in complex ways. If Holm 15A grew through repeated dry mergers, it might have accumulated a black hole that is exceptionally massive relative to some galaxy properties, not because the black hole broke the rules, but because the host grew differently than typical bulges. This idea has consequences. It implies that the high mass end of black hole demographics could be shaped more by environment and merger history than by self-regulated accretion alone. It suggests that the largest black holes may be the record keepers of cluster assembly, their masses encoding how many massive galaxies were consumed by the central one over time. So, How do we test these possibilities more decisively? We return to observation, because even the most elegant formation scenario is only as good as its predictions. One route is improved spatial resolution for stellar dynamics. The ability to resolve the sphere of influence more clearly reduces degeneracy between black hole mass, stellar mass to light ratio, and dark matter distribution. Future extremely large telescopes with mirrors tens of meters across will deliver sharper images and more detailed spectroscopy. They will sample the velocity field across the core with finer spatial elements and higher signal-to-noise. That will allow dynamical models to be constrained more tightly. If Holm 15A's black hole mass is truly in the tens of billions, higher resolution should reveal a stronger and more localized kinematic signature, a distinct rise in velocity dispersion or higher-order features in the velocity distribution that cannot be mimicked by stellar anisotropy alone. Another route is to look for complementary signatures in the cluster's hot gas. If the central black hole has been active in the recent past, its jets may have carved cavities in the X-ray emitting gas. Detailed X-ray imaging can reveal these cavities, along with shock fronts and ripples that trace episodic energy injection. The size and energetics of such structures can be used to estimate the power output of the central engine over time. While this does not measure black hole mass directly, it helps map the relationship between the central black hole and its environment. It also tests whether feedback has influenced cooling flows, the inward drift of gas that might otherwise condense and form stars. A third route is gravitational waves, though not in the way most people imagine. The gravitational wave detectors operating today are sensitive to stellar mass black hole mergers, not to ultramassive systems, but future space-based detectors are designed to detect mergers of massive black holes. If the central cluster galaxies have grown by repeated black hole mergers, they should have produced gravitational wave signals throughout cosmic history. Detecting such events would provide a direct measure of black hole merger rates and masses, offering an independent constraint on whether ultramassive black holes can be built through mergers as frequently as required. There is also the subtle prospect of displaced black holes. If mergers impart recoil kicks, the remnant black hole could oscillate through the core, leaving signatures in the stellar distribution or in the position of any active nucleus relative to the galaxy's photometric center. Evidence for such displacement would support a merger-driven growth history. In a galaxy with a large, shallow core, the restoring force that pulls the black hole back to the center is weaker, potentially allowing longer-lived offsets. Detecting these offsets is difficult, but it is not impossible with high-resolution imaging and careful modeling. All of these observational routes share a common purpose: to reduce the reliance on any single inference and instead build a reinforced conclusion from multiple independent traces of the same central mass. And yet, even if every measurement confirms an ultramassive black hole in Holm 15A, the most important lesson may not be numerical, it may be structural. Black holes at this scale challenge the boundaries between galaxy and nucleus. When a black hole becomes a significant fraction of its host's core mass, the distinction between the galaxy's central region and the black hole's sphere of influence begins to blur. The black hole is no longer just a compact occupant of the center. It becomes a dominant architect of the innermost kiloparsec. Stars orbit in a potential that is partly galactic and partly black hole, and the core's shape carries the memory of past binaries. In that sense, Holm 15A becomes a laboratory for extreme gravity in a cosmological setting. It is not a laboratory in the sense of controlled experiment. We cannot adjust initial conditions or rerun cosmic time. But we can read the evidence that the universe has left behind in light and motion, and we can compare it to the predictions of our models. The black hole's mass is not simply a trophy number. It is a constraint on what the universe can build and on how it builds it. The journey therefore ends not with certainty, but with sharpened questions. How many ultramassive black holes exist, hidden in the cores of central cluster galaxies that appear quiet from afar? What fraction of the universe's black hole mass is concentrated in these rare giants? How did the earliest seeds form? And what conditions allowed some to become so dominant while others remained modest? And perhaps most importantly, do our models of galaxy and black hole coevolution remain valid at the highest masses? Or do they need revision to account for environments where mergers, not feeding, dominate growth? Holm 15A does not give us all the answers. It does something more valuable. It shows us where the edge of our understanding lies, and it offers a target that is both measurable and extreme. A diffuse galaxy in a distant cluster becomes the stage for one of the largest gravitational concentrations we can infer. Its core is shallow, its stars move too fast, and the simplest explanation is a black hole so massive that its horizon would swallow the scale of planetary orbits. To stand at the end of this investigation is to recognize that the universe still contains objects whose sheer scale tests our methods. We can infer their weight from starlight, reconstruct their influence from missing stars, and trace their history through the architecture of galaxies. But to truly confirm their place in cosmic evolution, we must extend our instruments, refine our models, and search for converging lines of evidence that turn estimated into measured with narrower uncertainty. And that is the forward hook. Because Holm 15A is not a final chapter, it is a waypoint. As telescopes grow larger and detectors become more sensitive, the same cluster core will be revisited with sharper vision. The motions will be measured again. The gas will be mapped with greater fidelity. The models will be tested under new constraints. In that future data, the universe will either reaffirm the presence of one of its largest black holes, or it will force us to revise our assumptions about how gravity and galaxies conspire at the highest mass scales.